Now the question here is this, that getting the model is equivalent to just finding out the values of the unknown parameters on the basis of given sample of data. Right. So the question here is how to know this unknown parameter. So from the statistics point of view, I can use here different types of estimation methods. And we have different types of estimation methods, like a method of maximum likelihood, method of least square, etc., etc. So you can use actually anything, actually whatever you want here. So for example, I try to give an example of a least square estimation. So now we assume that we have here n paired sets of observation, and we assume that they all are going to follow the model y equal to beta 0 plus beta 1 x plus epsilon. So I can write down for every pair of observation, I can write down this model to satisfy this equation y is equal to beta 0 plus beta 1 xi plus epsilon. Right. And so if you try to plot this thing here, actually it will look like this. Suppose these values, they are the observed values of the y's that you are observing in real life. And so actually it will look like this. If you have here x and here y here, it will here look like this if you try to get plot all this observation. What you really want, you want here model of the for y is equal to beta 0 plus beta 1 x, right? So this is going to be a linear equation. So if you try to find out it, this linear equation may be like this. So now the question is this, so how to find out this linear equation? So what you will see here, that these are the values which are observed, and this is the line which you really want to find, right? So now what we can see here, that you can see here that this point according to your line should lie on this line here, and this point should lie somewhere here. So you can see here these are the some random errors which are happening in every pair of observations. So definitely we would like to find out this line in such a way which is passing through with the maximum number of points and in which this random error is as minimum as possible. Right. Let me just take a break of half a minute. Right. Okay. So now the question is how to get it done. So whenever we are trying to find out the values of this parameters beta 0 and beta 1 by minimizing this vertical errors, then this is called as direct regression method. Actually, there are a couple of regression methods: direct regression, orthogonal regression, reverse regression, etc. But surely I'm not going to touch upon those things. So now if you try to see, you just want to find out the value of beta 0 and beta 1 in such a way such that this random error is minimum. Now this you see, now this random error can be positive or it can be negative, in the sense that okay, all those values which are lying above this line, their errors can be taken as positive, and all those errors which are lying below the line, those errors can be taken as negative. So if you try to take so now the question is how to find out the total error which is happening in this observation. So if you try to take here only the sum, so some errors are positive, some are negative. So possibly some may come out to be very close to 0, and that may indicate that the data has no error, which is not correct. So what we try to do here, that instead of taking the sum of the random errors, we try to take the sum of squares of these random errors. So the sum of squares of the random errors will come out to be here like this. Summation means if you simply try to replace here epsilon I by here yi minus beta 0 minus beta 1 xi. So now my option is, now my problem is very simple, that I want to find out the value of beta 0 and beta 1 in such a way so that this function summation epsilon I square or this f beta 0 beta 1 should be as minimum as possible. So now you can use any algorithm, you can use anything to find out such values of beta 0 and beta 1. But for us, one of the most common approach one can use is the principle of maxima minima. That you simply try to use the principle of maxima minima on this function and try to minimize with respect to beta 0 and beta 1. So that we try to do here. So in the principle of maxima and minima, we partially differentiate the function with respect to all the parameters. We try to put them equal to 0, and then we try to solve those equations to get their values. So I try to differentiate this function with respect to here beta 0, with respect to here beta 1, and we get here these two equations. Anyway, I try to solve these two equations by putting them equal to 0, and whatever are the solutions that are going to obtain from here, they are going to be the least square estimator of these parameters, right? Or they are also called as ordinary least square estimators of beta 0 and beta 1. So I'm not going to give you here the algebra, but if you simply try to solve these two equations, you will get the value of beta 0 as y bar minus b1 x bar, and the value of beta 1 here as sxy upon sx, which is indicated here by b bar. So now you can see here that this sxy is given by here this quantity summation xi minus x bar yi minus y bar. So now you have got the values of x and y. From there you can obtain here this sample means x bar, y bar, and then you can obtain this quantity sxy. And similarly here sxx, this is summation xi minus x bar whole square. So once you have the values of x1, x2, xn, you can compute these quantities. And definitely you are not going to do it, but your software is going to do all the job for you. But your job is to understand what is really this software is going to do, and how should you understand and how should you interpret it. So now given the values of x and y, you can easily compute this value of b1. Once you obtain here the b1, you can put it here and you can compute here the value of b0. So the values which of beta 0 and beta 1, which are obtained here by this on the basis of a given sample of the data here, they are indicated by here b0 and b1. So that is the basic difference between the nomenclature. Beta 0 and beta 1, they are the values in the population, and b0 and b1, they are the values in which are computed on the basis of the sample. So they are representing the value of beta 0 and beta 1. Now, the main thing comes here that what is the interpretation of this thing. So if you assume, actually this is our assumption that I will try to talk in the next lecture. We assume that the expected value of epsilon is 0. That means the population mean of this random error is 0. And that is not a very bad option in the sense, because when you are trying to collect many observations, some errors, in some of the observation, the errors are going to be positive and somewhere it is going to be negative. So if you try to take the sum over the entire population, there some may come out to be very close to 0. So in case if you try to look at this model here, so I can write down here expected value of y is equal to beta 0 plus beta 1 x plus expected value of epsilon, which is equal to here 0, right? And if you try to see here what is here beta 1 is simply the first derivative of average value of y with respect to capital X. So if you try to see what is the interpretation of this, this is simply going to indicate the rate of change in the average value of y when there is a unit change in the value of here x. So that is being indicated by this here beta 1. And what about here this beta 0? Beta 0, if you try to see, if you put here this x to be equal to 0, then this term becomes 0, and then you have here the value of only beta 0. And beta 0 is equal to expected value of y. So that means this beta 0, which is the slope which is the intercept term, that is going to indicate the average value of the outcome when all the input variables are taking value 0. Right. And beta 1 is the rate of change in the average value of y with respect to x. So beta 1 is indicating that what will be the change in the average value of y when there is a unit value change in the value of here x. So for example, if you try to see here, suppose if I take y to be the yield and x to be the quantity of fertilizer. So definitely, when you try to give the quantity of fertilizer to the crop, then you would like to know that if you try to give 1 kg of fertilizer, then how much the average value in the outcome is going to change. So that is being indicated by the value of beta 1. And in case if you don't give any fertilizer in the field, even then you are going to get some crop. So that is going to indicate that what is the value of your y, or the average value of y when all x's are 0. That means there is no additional fertilizer given over there. Right, so that will indicate the value of the intercept term beta 0. Right, so now if you obtain the value of beta 0 and beta 1 on the basis of the given sample of data, your this fitted model becomes y equal to b0 plus b1x. And if you want to know the value of y for a given value of here x equal to xi, then it can be obtained just by substituting it here x equal to xi, and you will get here this value of here yi. So these values of yi, they are called as fitted values. So now you can see here there are two values of y. One set of y values which you have obtained from the experiment, and second set of y values which you have obtained on the basis of the model that you have obtained. Right. For the value that you have obtained on the basis of this model, they are called as fitted values. Right. So in case if you try to see here, so when you are trying to observe a value over here, somewhere here, and this fitted line is somewhere here, so you expect that this point should be here on this line. So this difference which I have plotted here, here, or here, this is called as residual. So the difference between the fitted and observed values of y, this is called as residual. So obviously, means if suppose if all the values are lying exactly on this line, then the model is going to be the best fitted. So that means the model is the best fitted if all these random errors are going to be exactly equal to 0. Well, that's not practically possible. Right. So now let me try to take this example and try to find out all these things, whatever I have shown you here. So now first I try to plot this data here on say here x and y. So you can see here, this is here the scatter diagram that I obtained. That is very easy to plot. Simply use the command here plot xy. Right. Now if you try to see for this data, I have plotted here 4 possible straight lines. What do you think that which of the line is going to represent your data in the best possible? Right. If you try to take here the first case, so you can see here lots of points are here, and this point and this line is not really contributing with all the lines. Here, most of the points are here, and the lines is not passing through with them. Similarly, here there are lots of points, and the line is not passing them. But if you try to see over here, the line is passing through. Sorry, this is the line is passing through with the maximum number of points. But this I'm telling you only from the intuition, and we will see what really do we get after getting the equation of the line. So now I use here the command here lm white tilde x, that is the command in the R software to get this model. So now here comes the point that whatever the values which I have estimated here for the beta 0 and b1 here, like I say here as a b0 and b1, you are not going to use it, but your software is going to use it. But your job is to know that what is representing what. So you will get here this type of outcome, that one, it is their intercept term, and here this is here x. So now this value, this is indicating which is with respect to x, this is indicating the value of beta 1, that is v1. And how this value has been obtained? This has been obtained by computing this quantity. And similarly, if you try to see here this value, this is obtained by here y bar minus beta 0 x bar. So at least now you know that that these values are getting here, how you are obtaining them value and how they are being computed. And this is the screenshot of the same operation that you can also try yourself. But So, but now if you try to understand what this outcome is going to inform you. So as I said, uh, this was your here the basic model that you wanted to fit. Here it is lying here the value of here x 3.407. This the value of here this sxy upon sxx. And if you try to use this value over here, and if you try to find out sample mean, then this value of intercept term will come out over here like this. So now you can see here, you have obtained here the model. Now your model becomes here y is equal to beta 0 plus beta 1 x plus epsilon was your model, and now you have obtained it on the basis of given sample of beta, which is here y is equal to b0 plus b1x, right? This means here the marks are equal to 75.779 plus 3.407 into number of hours of study. Right. So, so in case if you really want to understand what is this trying to tell you, so you can see here, this is here coefficient here is 3.407. So that is indicating that if a student is studying for about 1 hour more, then on an average, the marks are going to be increased by 3.407. And surely, if this sign is positive or negative, that indicates if the sign here is positive, that means the marks are going to increase, and if the sign is negative, that means the marks are going to decrease. Right. And if you try to see here what is this value here, 75.77. So if you try to put the number of hours per week to be equal to 0, even then the student is expected to get 75.775 marks. Well, that is possible. You are saying only what you are studying in every week, but that student might be watching video classes, videos on different courses. He might be going to the library to study. He might. So there are different factors which are, and then the student might have attended all the classes, so he has to listen all the lectures, and possibly he is intelligent enough to attempt all the questions to get some this 75 marks. So that is the basic interpretation of this thing. And now if you try to fit this line 75.7 plus 3.4 times here x, it will look like this. And if you try to see here in this past one, this is the same line which I have plotted here. But at this time, that time, I didn't know which is going to be the best possible line out of those 4 lines. Right. Now, in this case, if you simply want to obtain here the coefficient, then in the R software, there is a command here. Simply you write here down your coefficient, COEFFICIENTS, and inside the parenthesis, you write LM, Y tilde X. So LM means linear model, and Y is the dependent variable, and X is the independent variable here. So you will get here only this type of outcome that you can see here on this screen. Right. And similarly, if you want to find out here the fitted value, that means you try to use the value of x1, x2, xn, use them in the fitted model, and then you try to obtain the value of here y. So if you want to obtain these values here, that's pretty simple. Simply use command here fitted dot values inside parenthesis lm y tilde x. So you can see here these are the values that you are going to obtain it here. So it is something like this you are trying to see here. If you try to put x equal to x1, then the value of y which you are going to obtain from the model, this is 191. But here if you try to see on this data, this value is coming out to be here 180. So actually the student is obtaining 180 marks, but your model is telling that the student is going to get here 190 marks. But it's not actually bad. Right, you have actually good approximation, and yeah, this is the R command by which you can find it out. And similarly, if you want to find out here the residuals, that means you want to obtain the difference between the observed and fitted values of y. So for that, it is something like here you can see here yi is the observed value and yi hat is the value that we have obtained from the model. So this will look like here like this. This is the model, and you try to obtain. You have the value of your observed value here yi, and you try to obtain the difference, and this is called as residuals. And in R, you can find out such a residuals by this command residuals, and inside the parenthesis you use lm y tilde x, and you can see here this is how there are 20 observations, so there are 20 fitted values, and hence there are 20 uh, these residuals. And you can see here in some cases this residuals are quite high, and in some cases they are quite low, right? And you can see here. So now it depends on that what form of you have, form of the model you have assumed to put your data. If you try to change the form of the model, these values are definitely going to change. Okay, and this is here the screenshot. Means if you try to do it yourself, you will get the same outcome. Right, okay. And then after this, once you have estimated the values of beta 0 and beta 1, definitely they means they are the population values, and you are trying to estimate them on the basis of the given sample of data. So that will also have some variability. So the variance, well, so this B0, B1, etc., they have their variances and covariances also, but I'm not going to discuss about them. But my idea is to give you an idea that how are you going to compute the standard errors in these cases. So if you try to find out the variance of beta 0 and the beta 1 hat, that is the variance of B0 and B1. And if you try to find out their values on the basis of given sample of data, that is the standard, their estimators, their forms will come out to be here like this. Well, I'm not giving you here the detail, but I'm simply trying to give you here this option. And if you try to take here the positive square root of these two quantities, they will give you the standard error of B0 and the standard error of B1. Right, and if you want to know all these things, then you have a command here, summary command, summary with lm y tilde x. And if you try to do it here, you will get here like this. Well, I will be talking about such an outcome and different aspects of this outcome in the next lecture, but here I can give you this idea. Right. If you try to see here, this column here in this outcome will give you the standard error of intercept term estimator and slope parameter estimator. Right. So, right. And then, yeah, means if you, and then when you are trying to observe these observation y1, y2, yn, they are also random variables. So if you want to know that how much is the process variability in the data, then you need to assume that variance of y is equal to sigma square. But surely that sigma square is also unknown to us. So if you want to know that value of sigma square, that can be obtained here by this quantity SS residual divided by n minus 2. And yeah, so that means SS residual is that if you try to take this summation of epsilon I hat whole square, that is the sum of square of residual and divided by here n minus 2. Right, okay, so this will give you the value of here, the variability in your data here. And if you try to take the positive square root, it will give you here the residual standard error. Right, there are a couple of things more here in this slide that I will be able to explain you in the next lecture when we try to talk about the multiple linear regression analysis. Right, so you can obtain these values. Things have been actually obtained, right? And now you also know that how are you going to really understand that what are the different values of beta 0, beta 1, etc. Right. So at this moment, I would stop here, and it means I was just trying to give you a brief idea that how are we going to proceed further, and I have given you, because I have here only with two parameters, beta 0 and beta 1, so I can show you, several things clearly. But in the next lecture, I'm going to consider here more than two variables, so we will have more parameters. So it may not be possible for me to show them so clearly, but I will have some only value, and that you have to think in your mind that, okay, this is the value which is possibly going to represent such a thing.